Bismillah Rahman Rahim. Dear students, we today talk about the AVL tree and its proper concept and how to construct it, how to actually balance our binary search tree. So we were saying like we have if you have a binary search tree, like say for example we got 30 here, then we got 20 on this side, and we got 10 on this side, okay, and maybe we got some 25 on this side, and we got some say 50 on this side, and we got 40 on this side, and we got, say for example, 55 on this side. Okay, so this is my binary search tree. Okay, now if the data doesn't come like that there is 30, then 20, 50, but if there were 1 2 3 4 5 6 7 nodes here, but if the data comes like this: 30, 40, 50, 60, 70, 80, 90, and so on. Okay, now if we have a data like this, it will be all like 30 on this side, then 40 on this side, because 50 is greater than 40, it has to be on the right side, then 60, then 70, then 80, and then 90. Now if you see, the height of the tree will be the number of nodes. If the number of nodes is n, say 7, the height of the tree is 7. So if you have to find 90, for example, you have to go for a linear search. You can't apply the binary search here. Okay, you can't apply the tree structure searching here, where the binary search tree, which was going like, if we want to find, say for example, 55, we see 55 is greater than 30, so left subtree we do not have to search. Okay, we have to search the right subtree, and in a right subtree, now I come here. So first iteration was here, second iteration was here. So if I am trying to find 55, that has to be greater than 50, so I got it. So just two iterations took me to search the 55 in this scenario, if we have a 7 nodes. But if it is a 7 nodes and we're going to find the last node, okay, it will take me the n. So that is the difference. Okay, in a binary search tree, the complexity was big O of log n. Log n, what is log n? Because if we say like 2 raised power something is equal to, say for example, 32, so I want to find what is this, what is 2 raised power this. So we do log of 32. So log to the base 2 of 32, and that is equal to 5. So that means 2 raised power 5 is 32. Okay, so we do log of this. Say for example, 2 raised power something equals to 16, and I want to find what is this 2 raised power what. So if I do log of this 16 to the base 2, it is 4. So that means 2 raised power 4 is 16. So we can write it like this way or this way. That means the height of this tree is 7, for example. 7 plus 1 is 8. So how much is 2 raised power 3 is 8. Or in other words, I will do log of 8. I do log of 8, that is 3. The height will be 3. Okay, and the maximum, the complexity of this will be log of n. So whatever the n is, do the log of, if the n is 32, do the log of 32, that is 5. So at the max I will have a 5 iterations to do in this, to search or something. So same way, if I have a 16 nodes, I will do log of 16. So if the n is 16, if n is equal to 16, that means I have 16 nodes, so I will do log of 16, that is 4. So at the max, the complexity will be the 4 iterations I have to take to search something. So that is why, now is this a binary search tree? Yes, this is binary search tree, but this is skewed. This is right skewed binary search tree. But what is the complexity in this case? The complexity in this worst case scenario becomes log of n, because if n is, say for example, 16, I have to take 16 turns, in worst case, to find a particular last node, for example. If n is 15, if n is 20, I will take 20. So whatever the n is, that will be my complexity. So this is the complexity of big O of n in this case. So what we are saying is, we do not want to allow the skewness. We want to create this balance the binary search tree has. So, but this is also binary search tree, right? This is not, I can't say this is not a binary search tree. It is a binary search tree, right? But AVL tree doesn't allow this skewness. Okay, so we do not allow this skewness. So what we do is, we do rotation to remove this skewness, so that it becomes always balanced. So we are trying to balance the height of the binary search tree. So when you balance the height, the left subtree and the right subtree, they should be balanced. It should not be. So how much, that what we call as the balancing factor. We call it as a balancing factor. The balancing factor can be either 1 or 0 or -1. That means if we have, say for example, some root node and it has attached some, say for example, left subtree and it attached some right subtree. Okay, whatever the nodes there can be 10 nodes, 20 nodes, 100 nodes, and same way in the right subtree. It's a right subtree, this is a left subtree. Okay, now whatever the height of this left subtree is and whatever the height of this right subtree is, if I subtract them together, if I say height of left subtree minus height of right subtree, that should be either 1 or -1 or 0. If it is coming so, then I say this is balanced. If it is not coming so, then this binary search tree is not balanced. So we will balance it by rotation. So we will do rotation. Okay, so we will see that how we do the rotation. But the thing is that why we are doing that? To remove that skewness. Why we are doing that? So that our complexity will be big of log n, not n. Okay, okay. Say for the nodes we got is we got the nodes here is like 60, 50, 40, 30. Okay, say for example 70. Okay, let me put the 70 here. 60, I will put here, after 60 there will be 70. Okay, then 50, 40, 30 and so on. Then when I put up the 60, I will put up the 60. So whenever I put a node, I will check the balancing factor. Okay, all the time it should be 1 or 0 or -1. Remember that. Now this is my node 60. Okay, so what is the balancing factor here? Balancing factor definitely is 0. Why is 0? Because it is left subtree, it is 0. Right subtree is nothing, 0. So 0 minus 0, because we say left subtree minus right subtree. Left subtree, there is no left subtree right now, so that is 0. Right subtree, height of right subtree is 0. 0 minus 0 is 0. So it is 0. Balancing factor is 0. So it is allowed. Right? Now after 60, I am going for 50. Now 50 is lesser than 60. We know binary search tree, it has to be on the left side. So if it was like 60 here, for example, now 50 is to be attached on the left. I chuck the balance factor. If the balance factor doesn't come like this, then I go for rotation. Right? Right now I chuck the balance factor. I see balance factor. What is the balance factor of this? Balance factor of this is left subtree height is 1 and right subtree height is 0. 1 minus 0, that is 1. Okay, it is 1. That's perfect. Now what about the 50? It is left subtree is 0, right subtree is 0. What is balance factor here? Balance factor is 0. So the balance factor of 50 is 0, balance factor of 60 is 1. That is both allowed. Okay, so I can allow it. Now let us go for the next node, that is I should have gone for the 70 first. Let me put the 70 here. Okay, let me put 70 here now. So the 70 was here. Now I have to put on the 70. So this is 60 here. Okay, and 50 is also already here with the balance factor of whatever it was. Now I am putting 70. 70 is greater than 60. Where will it go? It will go to the right of 60. So it will go here. 70 is here. So what is the balance factor here? Of 60, balance factor is, because left subtree is 1, right subtree height is 1, 1 minus 1 is 0. So that is 0. What is the 50? 0 minus 0. Balance factor is 0. 70. Left subtree is 0, right subtree is 0. Balance factor is 0. So all are having 0 balance factor. So it is AVL tree. It is AVL tree. No problem right now. It is AVL tree is also binary search tree. Binary search tree is also binary tree. Alright. I told you yesterday that AVL tree is nothing but a binary search tree. And binary search tree is nothing but a binary tree. AVL tree is only thing is that AVL tree is the height balanced binary search tree. Okay. Now after that comes 40. Now we have to add the 40. So we have 60 here, 70 here, 50 here. So let me put up here 60 here. Then I got a 50 here. And I got here the 70. Now I have to add up and I have to recalculate now by these balance factors. I can't keep it same because it keeps on changing while we add. So 40 is lesser than 60. Will it go to the right or left? It will go to the left. Okay, it's coming here. But here is 50. Is 40 less than 50 or greater than 50? It is less than 50. So it has to go on the left of it. So I have say 40 here. So what is the balance factor of 60? Let me see what is the balance factor of 60. On the left subtree there are height is 2. Okay, and right subtree height is 1. So 2 minus 1. 2 minus 1 is 1. So it's perfect. Balance factor is 1. We have no issues. What about the balance factor of 50? For the 50, left subtree is 1, right subtree is 0. 1 minus 0 is 1. So for 50, balance factor is 1. That is perfect, no problem. What is the balance factor of 40? 0 minus 0. So balance factor is 0. No problem, because 0, 1 and negative 1 is allowed. What about 70? 70, left is 0, right is 0. So balance factor is going to be 1. So no issue right now. So until then, this is the AVL tree, balanced, height balanced AVL tree. It is a binary search tree. It is a binary tree. No issues whatsoever. Now when I add the 30, now let us see, this is 60 here, and I have got a 50 on the right, then I got a 40 on the right, and I got now the 30, because 30 has to be here. Why? Because 30 is lesser than 60, lesser than 50, lesser than 40, so it has to go on the left subtree. So it's going on the left, and on right side I got a 70. Now let us check for the 60. Now 60 has how many here? How many? What is the height of the left subtree? 1, 2, 3. Okay, so I got a 3 on this side and 1 on this side. So 3 minus 1 is 2. So balance factor is 2. So balance factor is coming 2, which is neither 1, neither 0, nor negative 1. So that means this is not an AVL tree. Now this guy needs rotation. Okay, it needs rotation to get height balanced. Now because you're getting skewed. Now the moment the height left subtree minus right subtree, height of left subtree minus height of right subtree, it becomes not 1, 0, negative 1, it is greater than something like 2 or 3 or negative 2 or whatever, which is not 1, 0 or negative 1. That means it's getting skewed. When it gets skewed, the complexity increases. Okay, because now I don't want this skewness, so I need to keep it height. So यहाँ पे height की balance खराब हो गई, so I need to balance the height. How we do the balance of height? Using rotation. So there are 4 types of rotations, and we will see this now. Now in a rotation we need to identify जो insert node किया आपने, जहाँ पे आपको insert node किया, क्योंकि हर insertion के बाद you have to check for the balance. So you have to see which node, well, going from that node which is inserted recently and going up towards the root, which node has got the balance factor not, which is not coming 1, 0, negative 1, so which is having a balance factor, not allowed balance factor, I could say. So it is 2. So this 60 has a 2. Okay, maybe sometimes you go up and this root, this node comes up, the balance factor whose balance factor is not 1, 0 or negative 1, allowed balance factor, which has a wrong balance factor. So then you have to identify that node. So you will go from the root, the node which you inserted. So here I am inserting this node. I will go from here and try to see which node, okay, on going towards the root, has the balance factor not allowed. Okay, and there I apply rotation. Okay, now I told you there are 4 types of rotations. First is, say, left rotation. Okay, there are, the rotations are of 4 types. We have left rotation, we have right rotation, we have left right rotation, and we have right left rotation. So what are these rotations? Now we understand them thoroughly. Let us take a first the left rotation. Okay, this is LL rotation, or left rotation. Say for example we got the nodes here, we have here is like we got a 20, then after 20 we have to fill up the 10, then we have to fill up the 5. Okay, now 3 nodes I have, so for example, so I am saying 20. Okay, I put up the 20 here, that's a root node, and balance factor is 0, 0, because left is this. Now after the 10, now 10 will go, is a lesser than 10, where it will go? It will go here, 10. Balance factor is, for this balance factor is 1, 0 is 1, allowed. For 10 it is 0 minus 0, 0, allowed. Now 5, now I insert the 5. The moment I insert the 5, the balance factor of 20 is disturbed. Why? Because on the left subtree is a 2 height, and right subtree is 0. 2 minus 0 is 0, so balance factor is equal to 2 for this. So the moment I inserted 5, balance factor of 20 got, for 10 it's okay, it is 1 minus 0, that is 1, balance factor is 1. But when I go from 5 onwards and I see the node towards the root, I go, and I'm seeing that 20 is getting having the imbalance factor. The balance factor is 2, that is not allowed, so it is a candidate for rotation. Now I am seeing here that I have here the two things, one is the left, another is the left, because both nodes are on the left side, the right side has nothing, right? So here I have in both sides left, so it is the LL rotation. Now how to do the rotation of it? For LL and RR they are same, because for left and right we need only one rotation. For left and right we need two rotations. You keep that in mind. Now if we have a left and right, so what should we do? Okay, in left as well as right, you find the A and B. You find the A and B. Okay, then make A as a child of B. So for this is the tip for solving this, tip or shortcut for this. For I'm saying left and right rotation, find A and B and make A as child of B. Okay, and who is A, who is B? Because I got here two, left and left, so it is a left rotation, because on the 20 which is having the balance factor, wrong balance factor, I have got the nodes which is 5 was on the left of it and to the left of it, so it is a left rotation. Okay, so the node in the contention, the node in the which is having balance factor wrong is A. Let me change the color of the pen. Now this is my A and this is my B. Okay, so what I do for left and right rotation, simple, make A is who is A is the one who has a balance factor wrong, okay, and B is the next node after it. What I will do is I will make the A as a child of B. Now make this 20 child of 10. So what you do here is you will do the rotation. I will show you. Let me erase this. Right. Okay. So what you will, how you will do this? You will do a little rotation here. Okay. You will twist it. You will make this 10 as a pivot. Say B is my hinge. Just पे rotation होगी. Okay. And you rotate this one. You rotate this one and you get it down. You get this bond. You will get it down and rotate it. You will rotate this 20 and 10 on this line. You will rotate it like this. It goes here, it goes here, it goes here, and it comes here, and it becomes the child of this 10. So it will become like this. 10 is here, now 5 is here, and 20 is here. Okay, now this was the A and this was B. Now A become the child of the B, and it is voila, it is balanced now. And as you could see, it's a binary. Is it binary search tree? I do not have to break the rule. Yes, it is, because 20 is greater than 10, it has to be on the right. 5 is less than 10, it has to be on the left. And what is the balance factor of 10? 1 minus 1, 0. Balance factor is 0. What is the balance factor of 5? 0 minus 0. Balance factor is 0. What is the 20 balance factor? Balance factor is again 0. So it is perfectly height balanced. So that skewness is gone. Right? Now it becomes height balanced. So what you have to do? You have to identify the which node is not in the balance factor, call it A, and the next node to the left, if it is left, okay, I'm talking about left, even though there's the same policy will apply for the right, we'll see it in a moment. Okay, now balance factor is what? Balance factor is, say for example here, this one has a balance factor of 2, call it A, the next node on the left, call it B, and make A child of B. That means rotate it on this, rotate it on this node, and when it rotates, it goes down like this. Even you rotate it like this, okay, you rotate it like this, down, okay, it goes down, the 20 goes down, okay, it comes here in my I guess in the video it comes in a wrong way. So 20 goes like this, okay, so 20 goes like this down, and simple, you find A, you find B, and make A child of B. That is the only thing you have to remember. Now let us go for the right rotation, which will be same. Say for example, the node we got here is we got here, say for example, we got 50, 60 and 70. If this is the scenario, so this is my 50, the 50 comes here. What is 60? 60 greater than 50, it has to be on the right of it. Okay, what is the balance factor? Balance factor of here is 1, this is 0 minus 1, that is -1, balance factor is -1, all right. 60 balance factor is 0, all right. Now it goes to the 70. Okay, now 70 is greater than 60, it has to be on the right of it, so it is right skewed tree now. And I am saying, what is the balance factor of this? Left subtree is 0, right subtree is 2. 0 minus 2, it is negative 2. So balance factor is negative 2. So that problem, because our balance factor has to be either 1 or 0 or negative 1, but it is coming negative 2, so that means problem. So the moment you inserted 70, okay, you will see the balance factor of the node which is towards the root, you move towards the root, okay, and you see the balance factor whose balance factor is not among these. So this is the 50, and you say, oh, this is a problem, I have to, this is not my AVL tree, I have to height balance it by rotation. Now you will see which rotation is here, and I am seeing on a 50, it is on a right of it, it is on a right of it, so I have got a right rotation here. So it's a candidate of right rotation. Again, you have to do same. So what you will do same, you will try to find A and B. Okay, who is A? A is the guy which has the wrong balance factor. This is my A, and the next node is B if it is right. And you will make A child of B. Find A and B and make A child of B. So make A child of B. You will make A child of B. So how will do? Now here you have to do in a right, you have to do anti-clockwise rotation. In left, you have to do clockwise rotation. You have to move it clockwise. Okay, but in the left, you have to do right, you have to do anti-clockwise rotation. So you will rotate the B. On the B, you will rotate this node. Okay, you will rotate this guy. You rotate this guy on the B and get it down like this and make it here. Okay, get it down. So what we will do is we will get it down like this and make it 50 here, right? So overall it becomes like this. It is 60. So 50 comes here and 70 comes here, and everybody is happy. Balance factor here 1 minus 1 0, balance factor 0, balance factor 0. So it's a height balanced tree. Now this is my AVL tree. Now this was not my AVL tree because it was having not the balance factor right, it was having negative 2 balance factor here. And the candidate of rotation, it was right, the second rotation. So in both cases, left or right, you have to find A and B. A is who jiska balance factor not correct, and B is the next node, and then rotate. If it is right, go for the anti-clockwise rotation. If it is left, go for the clockwise rotation. ठीक है ना, क्योंकि 60 को आप, you can't go clockwise rotation here. 60, you can't, 50 cannot go to the right of the 60, 50 has to go to the left of 60, right? Because 50 is smaller than 60, it has to be on this side. Very good. Now we move on to the next rotation, that is left right rotation. Now for left right and right left rotation, okay, say for example firstly we talk about the left right rotation. Okay, this is my left right rotation or right left rotation. In both these cases, you either do the two-step or you can do the single step. So I will show you the both methods, the two-step process or two rotations, or in a single step you will do the both rotations. Okay, then if you become expert a little bit, then you can do the single step, in fact. Okay, say for example we have data like this. Say for example we got 30, 20 and 25, the data like this. Okay, so what is coming? The 30 will to 30 go, 30 will come here. Okay, the root node. Now balance factor is 0, 0 minus 0. Okay, now 20 go to the left of it. Now balance factor of this is 1 minus 0 is 1. This one is 0 minus 0 is 0. All right. Now why will the 25 go? 25 will go to the left of 30 and to the right of 20. Now it is going to be 25 is here. So what is balance factor of 25? Balance factor of 25 is 0 minus 0, that is 0. Balance factor of what is this, 20? The balance factor of 20 is 0 minus 1, that is negative 1. What is balance factor of 30? 30 is the 2 on the left side, left subtree is 2 height and right subtree is 0. 2 minus 0, that is 2. Now balance factor is 2, therefore it is a problem. And when I see the problem, it is coming, the 20 is coming to the left of it and then 25 is coming to the right of it. So it is an LR. So we need what is called as an LR rotation. Here what we do is we first find ABC. Okay, we find three things, A, B, C. So for LR rotation or R rotation, find A, B, C. A is the one which has the problem. That is, A is this one. So let me change it to the black now. Okay. Now this is my A. The B will be the second node, which is on the left, and C is on the right. Now, in a first step, in a first rotation, what I do is I convert this LR rotation to the LL. I convert this LR to LL. So what is that? So for that, I will see the B and C. I will rotate this B and C. The first step. Okay. The first step, either we do this way or we do the single step. In the first step, I am saying the first step is convert LR to LL. How? We rotate, or we make we rotate at B, or we say simply we can say make B child of C. Now make B child of C. Now what I'm making is B, make B child of C. How I can do the make B child of C? I will rotate there anti-clockwise. I will get the C or top and 20 down. So it will become like this. It was 30 here. Okay. It is becoming here now, the 25 comes here and 20 becomes the child of it. Now as you could see, it becomes LL. Now this is my A, this is my B, and this is my C. Okay. Now this becomes left. So we know when it becomes left rotation, we know the same thing. We have done it. That make, what we do now, if this is A, B, C, now it's a left rotation. What we do, we have A and we have B. We make A child of B, right? So what we do in a step second is we apply the left rotation. Okay, apply LL rotation rule, that is make B A child of B. Make A child of B. That means what you do is you will make the A child of B. That means you rotate here, you rotate the 30, get it down, so it becomes like this. So 25 comes here, okay, and this is 30. In fact, I should not say make, because I was having A, B, and C. This was B. B was my 20, and C was my. So let it be. C has gone here now. B has gone here. Okay, I will keep the same A, B, C. So A, C, B. So therefore, make the A child of C, not B. Huh? I should say make A child of C, because this was C, because I rotated it here ना. Get the C top, 25 यहाँ आ गया और 20 नीचे आ गया. ठीक है ना? So now I will use the left rotation rule, where I find these things. Now A will become the child of C. So 25 comes here, 30 goes down. So 30 go on this side and 20 go on this side, and everybody is happy. Everybody's balance factor is 0. So this is my AVL tree, and that too balanced, right? I can do same thing in a single step. Okay, if I want to do same thing in a single step, how I will do that? Let me go to the next slide. What nodes I had? I had 30, 20, 25. Okay, so I am having here 30, 20, and 25. So I put up 30 here, I have to get 20 here, and I have to get 25 on this side. Okay. Okay. Now this is the balance factor here is 2 minus 0, that is 2. So balance factor is 2, so there is a problem with this. So I have to rotate, and it is a left and right rotation, LR rotation. Okay. In this case, I could say the second, which is the shortest path, shortest way of doing things, is find A, B, and C. This is my A. Let me change the pen to the red now. Now this is my A, this is my B, and this is my C. Okay. So if I'm saying find A, B, and C, and then make A and B child of C. What you do is make this A and B child of C. So that means the C becomes the root of here. Okay. So C comes there where the 30 was there, and make this A and B child of C. How will make A and B child of C? Now 30 will go on to the right and 20 will go on to the left. Simple. And we are done. Okay, if it was left right rotation, just find the A, B and C and make A and B child of C. So how will you make A and B child of C? A is 30, which is greater than 25, it has to be on the right. Okay, and 20 is the lesser, so it has to be on the left. Simple as it is. Or if you can't do this way, then do this way, that first convert this into the LL rotation. How? You rotate the B and C. Okay, you make C the child of B the child of C here. Okay, then you become the B the child of C. That is it, it becomes LL rotation. And for LL we know you have to make A the child of C. Or in simple terms, you will make 25, which was the C, and you will make A and B child of the C. That is here like this. So A, B, C. So C is here, which becomes our father of them, and B and A becomes its kids. Simple as it is. So same is with the right left rotation. So that's the last rotation we are here having here. That is right left rotation. The same principle applies for the right left rotation, either the two rotations or the single thing. Say for example we have data is 50, 60 and 55. So 50 will come here. Where was 60? 60 will go on to the right of it, and then 55 has to go to the left of the 60. That is 55. So what is happening here? Again, this has the balance factor. The moment you apply the 55, the balance factor of 50 goes wrong. Why? Because right subtree is, height of the right subtree is 2 and left subtree is 0. 0 minus 2 is negative 2. So balance factor is negative 2. So we have to apply rotation, and I am seeing it is on the right of it and it is on the left of it. So it is RL rotation. So when it is RL rotation, you will convert it, you will convert RL to RR. Okay, like we converted LR to LL. So we keep L there and make this R as a L. And here I keep the R there and convert this L to the R, RR rotation. So you find A, B and C. Okay, so how you convert this RL to RR? You will rotate, you will make the C and B, you will make the B child of C. So that is, you have the 50 here. Now you make the, rotate it here, you rotate this guy to the 60 and get 60 down. So you got a 55 here. Okay, and 60 has to be on the right of 55 because 60 is bigger than this. So it goes down and 55 comes here, it rotates like this. So it becomes now RR. In the RR we know if this is A, B and C, now A, the C is here, B is here. Now make, when this is ACB, what you will do for the RR rotation? You will make A child of C. So that is 55 comes here. Okay, now 50, इसको ये rotate हो जाएगा, ये वाला बंदा नीचे आ जाएगा. So 50 will go down and 60 will go here. So it is balanced now, pretty balanced. Or you can do in a single step. So you got 50 and you got 60 and you got 55. So if this is a scenario, you will make, this is A, this is B and then C. You will make A and B child of C. Simple. You will make A and B child of C. So if it is right left or left right rotation, right left or left rotation, you will make A and B child of C, and you will keep the binary search thing in your mind that the smaller one go to the left and the bigger one go to the right. So that means the C will become the father, that is C will become the father, that is 55. And now 50 has to be to the left of 55 and 60 has to be the right of this. So simple, this way it is simple. So let us adapt not this one, let us adapt this one. We say if it is left rotation or it is left right rotation or it is right left rotation, find A, B and C, find A, B and C and make A and B child of C. Simple rule. Make A and B child of C. So find A, B and C. A is who? A is the one which is whose balance factor is getting wrong. It is having a 0 on the left side and a 2 on the right side. 0 minus 2 is 2. So balance factor is 2. So this was in the wrong balance factor. So that is my A. The next node is B. Third node is C. Now what I do is C becomes the parent. C becomes the parent and A and B becomes its child. Simple. make A and B child of C, and use the common sense that if it is 55, so lesser one, say for example we have the another node, say we have here, say for example we have here 20, and we say 25 on this side, and then we got 22 which is on this side. So this is the right and left. So nothing to do, find A, B and C, make C as parent, that is 22, and make 20 and 25 their child. So if it is 20, where will go 20 go on 22? It will go to the left, and 25 it will go on the right. Bingo. So we are done. So same way, if it is 20 and we had say for example 10 which was coming on the left side, and then I got a 15 which is on the right side, so it is left right rotation. So left right, find A, B and C, make C father, and 20, so is 20, will 20 go to the left or to the right? It will go to the right, and 10 it will go to the left. Bingo. So make A and B child of this C. Simple. So it's balanced. So apply these four rules. So okay, if it was left left, it was right left, or it was whatever it was, apply these four rules and you can do for the whole tree. Now next video we'll do a example of a big tree and apply all these four rules. Hope you got it. If you don't got it, just recap it, do it, put the things on a copy, try to do it of your own, make these examples of your own, and you will be good to go. Okay, so then see you next time with an example of AVL tree. Until then, masalama.